All right. Class recording has started, everybody. So yesterday we continued our discussion of chemical bonding, and we talked about and we reviewed some of the things about bonding, such as a bond is an attractive force that holds atoms together, and atoms bond with each other in order to get to a low energy state, and they do that by achieving that stable electron configuration, 8 valence electrons, all that fun stuff, right? None of these things change, right? Why atoms bond, what they're looking to accomplish, what a bond is, that's all exactly the same thing. But we got into how that happens is a little bit different. And so when we talk about ionic bonding, we're talking about transferring electrons between atoms. But when we're talking about covalent bonding, now we're talking about sharing electrons between atoms. Again, we're still trying to achieve that stable electron configuration, those 8 valence electrons, just a different way of accomplishing it. So another way we can look at it too is our different types of atoms. And we kind of got into this right at the end of class, right? What types of atoms bond ionically? Metals and nonmetals, because in order for there to be a transfer of electrons, one atom has to be looking to lose electrons and another atom has to be looking to gain electrons, right? But what types of atoms have to make up a covalent bond? 2 nonmetals, because if we're going to share electrons, they both have to be looking to gain electrons, right? And so we talked about that, right? Atoms are going to share valence electrons so that they both achieve that stable electron configuration. And we looked at this picture here of some different ways that we can represent that covalent bond, right? We drew fluorine and fluorine, and we drew Lewis diagrams of them and showed how the pair of electrons get shared between the two of them. Here's hydrogen and hydrogen, but right here we're sharing 2 electrons, right? This is okay, even though there's only 2 electrons there, because we talked about the idea that smaller atoms only need 2 electrons to be stable. Does that sound familiar, right? Because 1s and there's no 1p, blah, 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 right? Okay. We talked about the idea that when we are drawing bonds between atoms, a lot of times we will use this line connecting them. That line represents a pair of electrons, right? So whenever we have the line, it's always going to represent 2 electrons that are being shared between those 2 atoms. And those are the 2 most common ways that we represent covalent bonds, okay? When we end up with 2 atoms that are joined together by covalent bonds, we call them a molecule, right? Sorry, I should say 2 or more atoms joined together by covalent bonds, right? Here is a molecule between hydrogen and chlorine. Here is a molecule between 2 hydrogen atoms and an oxygen atom. Here is a molecule of 3 hydrogen atoms and 1 nitrogen atom, right? They're all held together by covalent bonds because they are nonmetals bonded together with nonmetals. Okay? Good there? All right. So a specific type of molecule that we talk about. Oh, why are we here? All right. A specific type of molecule that we talk about is a diatomic molecule. Okay? So, like its name suggests, if you know atoms, right, they might be one to help out, okay? Diatomic molecules are molecules that consist of 2 of the same kind. Find your clip on the blue tray. 2 of the same kind of atoms. So yesterday in class, we drew a diatomic molecule of fluorine, right? Because fluorine was bonded together with fluorine, okay? That's a diatomic molecule. And what we find out is that, well, here's chlorine and chlorine. Does it make sense that if fluorine bonds together with fluorine, chlorine should bond together with chlorine? Why? Same group, same family, right? That means they have the same number of what? Valence electrons, right? So if fluorine does something, chlorine's probably going to do it too. Sammy, go ahead. Hydrogen is definitely considered as a nonmetal, even though it is on the far left hand. It usually shows up on the periodic table way over on the far left hand side. Hydrogen is definitely a nonmetal, even though it has one electron and that therefore it has one valence electron. It behaves. It's not like a metal, right? It definitely. Obviously, its physical properties are much different than a metal, but also its chemical properties are different as well. So yeah, for our purposes here, hydrogen is going to be a nonmetal. Okay, and that also, it falls into this category as well. What we find is that if we look on the periodic table, there are 7 elements that will join together diatomically. Okay, these 7 elements will join together diatomically, even though there may be other elements in the same family as some of these. Not every non-metal joins together diatomically. Only these 7 do it. Okay? So that might be a good one to make a note of on that line underneath your outline, which are 2 of the same molecules, right? Okay. So there are 7 elements that join together diatomically. All right, good there? So we're going to use some of these diatomic molecules to introduce our last topic here at the beginning of covalent bonding. All right, so here we are, and just to review, right? Yesterday we looked at fluorine. Today we'll look at chlorine. Okay, chlorine 1, 2, 3, 4, 5, 6, 7. Here's another chlorine. 1, 2, 3, 4, 5, 6, 7, right? Each of those chlorines is looking to do what? Gain 1, right? And so we share this pair of electrons right here, and if we wanted to, we could replace that pair of electrons with a line to represent the sharing, and we look like that, right? That is a diatomic chlorine molecule. Okay? Good there? All right. So, at the bottom of your outline there, in the back of the outline, you have some space. It might be a good idea to draw some of these pictures. Chlorine, obviously, we drew fluorine yesterday on the front side, I think, right? So chlorine pretty much looks the same, so you don't necessarily have to draw that one, okay? But I would like us next to draw the Lewis diagram. Draw me a Lewis structure or a Lewis diagram for oxygen. Draw me a Lewis diagram or a Lewis structure for oxygen. All right, how's that? Good there? All right. Oxygen, based on its position on the periodic table, has how many valence electrons? It's got 6, so there's my 6 valence electrons, okay? So we know that oxygen is looking to do what? Gain 2, right, to get to 8. And we've seen how if we have, let's say, calcium, right? Calcium has 2 valence electrons. Calcium can give away those 2 valence electrons to oxygen and everybody's happy, right? But, right? Okay. Let's say the only thing around is another oxygen atom. Okay? Again, just like yesterday, will the red oxygen give away electrons to the blue oxygen so the blue oxygen can have 8 valence electrons? No, right? The red oxygen wants to gain valence electrons just like the blue oxygen does. Here we have a situation, right? 2 nonmetals both looking to gain electrons, right? So we can covalently bond. And we'll share this pair of electrons, all right? But we said that shared pairs count for both atoms. If we count up now, right? If we share that pair of electrons, that only gets read up to how many valence electrons? 7, right? So what's going to happen? They're going to another share, right? Okay. There's another pair of electrons here to be shared. Okay. Now they're technically sharing 4 electrons, right? So we have covalently bonded, but how many covalently bonds, or how many covalent bonds have we made here? 2, right? Each pair of electrons is a covalent bond. Here, there are 2 covalent bonds between oxygen. So we could represent this molecule like this. Right. Remember, each line represents a pair of electrons being shared. Okay? Good there? Draw for me a molecule of diatomic nitrogen. Talk to the person next to you. Draw for me a picture of a molecule of diatomic nitrogen. Discuss with the people around you. Go. All right, good, all right? How many covalent bonds exist between these 2 nitrogen atoms? 3, right? So we could represent that with 3 lines in between them, all right? Just like that, okay? So in both of these cases with oxygen and nitrogen, we've ended up with our atoms having, both of our atoms having 8 valence electrons. We just had to share more electrons to do it, right? Which is okay, because the end goal is to end up with 8, no matter how we get there. So in this situation, we refer to this as multiple bonds or multiple covalent bonds. Some atoms are held together by sharing more than 1 pair of electrons. And you can see from your outline, right, if we look at oxygen, how many pairs of electrons are, or how many pairs of electrons are these oxygen atoms sharing? 2. So what do we call it? It's a double bond, right? Because we're sharing 2 pairs of electrons, right? So a double bond is when 2 atoms share 2 pairs of electrons. That would be 4 electrons total, right? 2 pairs is 4, right? Nitrogen, sharing 3 pairs of electrons, is held together with a triple bond, right? Where 2 atoms share 3 pairs of electrons. All right, good so far? Okay. Go up the page a little bit and find the list of elements that forms diatomic molecules. Okay? Did you see the 7 elements that, or do you see the list of 7 elements? All right. So, hydrogen, right? Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those 7, okay? Which element is definitely non-metal that doesn't fall onto that list? One that you maybe think could or should? Hydrogen's on the list. Is there another non-metallic element that might fall on that list? Maybe one that's pretty important to us in our life here on Earth. Right? Okay. Carbon, right? So, how many valence electrons does carbon have? 4. 4 valence electrons. What? Carbon has 4 valence electrons. Is it possible for carbon to bond diatomically? Well, it's possible. So, if we end up like, if we look, okay? Come on. So here's carbon, right? And it's 4 valence electrons. If another carbon came along, theoretically, could this happen? What would we end up with?
Share them all.
Share them all, right? What would we call that then? It would be a quadruple bond, right? Because they'd be sharing how many pairs of electrons? 4. Would that get them to 8? Yeah, it would. But this doesn't happen, right? We never see a quadruple bond in nature. You tell me, why not? Right? Not necessarily, it's not necessarily a nucleus problem. It's more of an electron problem, right? If we look, remember we said that these atoms are sharing these electrons, right? How many electrons are there between these 2 chlorine atoms? There's 2 in this space, right? How many electrons are there between these 2 oxygen atoms? There's 4, right? What are electrons trying to do to each other? They repel, right? So, even though there's 4 electrons in this space, that's still lower energy than when they're not bonded. How many electrons are there here between these nitrogen atoms? 6. That's a lot of electrons to have in a pretty small space, right? So, why don't we end up with the quadruple bond? Too many electrons in one space, right? That ends up being a higher energy situation because all those electrons are trying to repel each other, right? And that doesn't work. So we never see a quadruple bond in nature. We only go up to triple bonds. And even triple bonds don't happen all that often, but they do happen, right? So yeah, if you were thinking to yourself, well, what about 4? Well, no, right? Could there ever be a 5? Yeah. A quintuple bond, if you think about it that way. 2 reasons, right? What's the first reason? Higher energy. What would be the other reason? It gets you to how many? It gets you to 10, and we don't need 10, right? Okay? Sammy, go ahead. No, because they it's kind of like they won't stay that way. How's that? Like technically we could probably make them come together, but as soon as we stopped pushing them, they would just fall apart because it wouldn't stay there. Does that make sense? You know, when we talk about have we ever or could we, the answer to the question is could we do something is always yes. All right. If we have enough energy to do it. That's kind of the thing, you know? But it's a matter of, will it stay that way? No, probably not. All right, is that good? Okay. So, when we talk about diatomic molecules, we have 2 atoms of the same element sharing electrons. And we said that's the situation we need to have covalent bonds because one atom is looking to gain electrons, another atom is looking to gain electrons. That's how we share. Okay? But what we find out is that we don't always have to have the same element. I think somebody asked, no, you didn't just put your water bottle away. You crunched it and made all that noise. And, you know. So, I think somebody asked yesterday, here's oxygen, okay? Could oxygen join together with fluorine? Could, right? This fluorine is looking to gain 1 electron. This oxygen is looking to gain 2 electrons, right? So this could happen. And that would work. Okay, no problem, right? Is oxygen done yet? No, right? If another fluorine came along, right? We could end up with that. That would work, right? This is not a diatomic molecule, but it is a molecule. It's a group of atoms held together with covalent bonds. Okay?
Which bond is the most common used?
Well, of what options?
Oh, covalent.
Oh, okay. Generally speaking, covalent bonds are going to happen more because, like, when we talk about life here on Earth, a lot of it is carbon-based and silicon-based, and so that those are non-metallic elements, and so that's going to be more, right? So, but we'll also see here in just a second that covalent bonds are actually important because of the way that they happen. It allows us to do some things. So, okay. Here, yes, we have 2 atoms or 3 atoms held together with covalent bonds, but they're not the same atoms. And so sometimes that leads to a situation where we have sharing, but it's not always equal sharing. All right? So let's take a look at the new outline that I gave you today. And let's jump straight down to electronegativity. Okay? I hope that you could fill out the first part, or letter Roman numeral 1. Okay? Chemical bonding deals with what? Valence electrons. It also deals with what? Energy, right? Getting to a low energy state, valence electrons, all that fun stuff, right? Ionic bonding is how do we transferring electrons, where covalent bonding is sharing them. Okay. But like I said, sometimes we may have a situation where electrons are being shared, but not always shared evenly. And so electronegativity. Electronegativity is basically a measure of how much does an atom want to gain electrons. All nonmetals want to gain electrons, but some want to gain electrons more than other atoms. Right? That's not what's written up on the board, but that's what electronegativity is. How desperate are these atoms to gain those valence electrons? Okay? And what we find out is that the closer they are to 8, the more desperate they are to get to 8, right? The most electronegative elements have the greatest attraction for electrons. And there are several factors that go into determining the electronegativity. Some deal with how many valence electrons does it have. But in that case, any elements that had the same number of valence electrons would have the same number of electronegativity, and that's not what we see. There's some size factors that go into it and everything else, and a scientist named Linus Pauling took all of those factors that affect how much an atom wants to gain electrons, ranked them, and assigned atoms a value from 0 to 4, with 4 being the highest electronegativity and 0 being the lowest electronegativity. And here is a periodic table, and you guys have this periodic table at the bottom of the front page of your outline, that shows the electronegativity values of all the elements on the periodic table. Okay? So, comments. What do you see about these electronegativity values? Frank, good.
How does the
Okay, so Frank, you're commenting about group 18, right? Okay, what do you see about most of the electronegativity values in group 18?
There's none.
There are none. Does that make sense?
Yeah.
Why?
Because they're still
They're stable. They're not looking to do what?
gaining.
Gain or lose. Electronegativity measures the gaining values, right? So why does xenon have a value? It's a size thing, right? Xenon is a really big atom, and so there are cases where it could gain or lose electrons based on what else is around it, okay? Your question then is, well, why doesn't radon have that? And the answer is I don't know. What else do we notice about some of these electronegativity values? Oh, go ahead.
Pretty much the top right corner of the most
Top right corner has the highest electronegativity. So what do we know about atoms up in the top right-hand corner up there? What are some things we could say about these atoms in the top right-hand corner? They're highly reactive, okay, because they're looking to do what, Sammy? Gain electrons, right? They have already a high number of valence electrons, not quite 8, but pretty close, right? Also, too, how big are those atoms? They're not that big, right? Remember, the closer we are to the nucleus, the higher there's like more attraction there, right? Because the nucleus is positive and electrons are negative, blah, blah, blah. So being small in this case actually helps it gain electrons, right? Where are our lower electronegativity values?
Bottom left.
Bottom left, right? What kind of elements are down there?
Alkaline.
They're metals, right? So they're already looking to do what? Lose, right? But these bigger metals, right? Those valence electrons are really far away from the nucleus, at least compared to other atoms, right? So hopefully, based on what we know about atoms and things like that, do the numbers sort of make sense?
Wait, so we can't necessarily just
We can, although it's not in a nice pattern like columns 1, 2, 13 through 18 is. Okay? Yeah, they get to 8, but it's not as in nice need of a pattern as all the rest of them are. So yeah, we're at this point, like I said, we're just going to kind of disregard those. Okay? So, Jack, go ahead.
Why does it look just like that? Starting with the MO and ending at gold. Why do those like so much higher than this one? They're right in the middle.
Okay. Oh, like these ones right in here?
Yeah.
That's not as big of a difference as you might think it is, okay? And two, so if you remember, Jack, remember like back when we had the chart that showed which orders the orbitals got filled up in? Once you get past 4s, now they start sort of mixing, like the D's and the P's all kind of, remember that chart? And they're all, so there's all kinds of mixing going on in there, and so like it's hard sometimes to tell which one is the valence shell and which one isn't. Like, so yeah, that's why there's inconsistency in that space. Okay. All right, so what does this do for us? Well, what we find out is by looking at the electronegativity values of the atoms that make up a bond, we find that there are different types of bonds. How big a difference there is between electronegativity values determines what type of bond it is. So first, we start with ionic bonds. What did we say happens in an ionic bond? So number 2, letter A, should be ionic in that space. Okay. What happens in an ionic bond? A metal loses electrons and a non-metal gains electrons. If we go back to this chart, right? Electronegativity is how much atoms want to gain electrons. If there is a big difference, like let's look at the value for fluorine, which is 4, and the value for sodium, which is 0.9, that's a difference of 3.1, right? That's a big difference in electronegativity. Fluorine very, very, very much wants to gain electrons. Sodium very, very much does not want to gain electrons, right? So if we take a look at the two electronegativity values, and the difference between them is greater than 1.7, we say that those electrons are completely transferred from one atom to the other atom. There is no sharing going on in that situation, because one very, very, very much wants to gain electrons, the other one not so much, and so we end up with electrons being completely transferred between one atom to the other. Okay? The next category, if the difference is between 0 and 0.4. Now remember, this is the difference between them. If the difference between them is small, the difference in electronegativity, what is that saying about those two atoms? No, not necessarily. What does electronegativity measure? What did we say it tells you? How desperate atoms are to gain electrons, right? Even in a case like fluorine bonding to fluorine, okay? Fluorine has the highest electronegativity of any atom. But, right, in this picture that we drew yesterday, does this fluorine want to gain electrons any more than this fluorine? No. They both want to gain electrons really, really, really badly, but not one more than the other. So they will share, and because they're both equally desperate to gain electrons, they will share those electrons nice and evenly. All right? And then finally, and this is where we start getting an influence into what type of bond it is and then what the properties of that molecule are. We end up with a polar covalent molecule, or bond. A polar covalent bond means that we are sharing electrons, but those electrons are not necessarily being distributed nice and evenly between those two atoms. Because one, if there's a difference in electronegativity values, one atom wants electrons more than the other atom does. All right? Does that make sense for now? Yeah. Okay. Why don't we call it a day there? We'll finish up this outline tomorrow. We may or may not get to naming things tomorrow, but that's okay if we don't. Okay?
Oh,